Hey everyone, so welcome to the Specialist Maths recording. How I plan to do this is mostly going to be similar to what I did for Maths Methods, so this will be going again at a much faster pace than what I was going at during the actual lecture that I delivered. Of course, again, because I know not all of you would have watched that recording, just as a reminder, remember that anytime you can always pause the video and just slowly try to digest what I said, at least for that slide only, before trying to move on. I do feel like with Specialist, every now and then, it's also somewhat necessary, I suppose, because, well, some of the questions are just much longer, and it's really hard to just look at a whole bunch of math and be convinced about it. You may need to write it out to really convince yourself that everything actually works the way you'd hope for it to work. But of course, in either case, if you have any questions about these, you can always just jump on the ATAR forums, ask me about it on our question thread. But yeah, I won't spend too much time blabbering on about this stuff. I've already talked about most of the stuff that we do at ATAR notes in the method video, so you can check it out there. But as a loose summary about two things I just want to remind you about with Ed Unlimited, remember that our free trial is still going for this online resource where you can basically get access to all of our publications. Of course, seeing as you're doing specialist math, you may also want to get the extra edge and get that one as well, right? So, it gives you more practice. And you also do get access to topic test publications for the Victorian equivalent, and also some HSC equivalent subjects as well, so you can use those as an extra study resource. And also, TuteSmart has already started, but our free offer for a 2-week trial is still ongoing right now. Remember to check that out at tutesmart.com. It's very comprehensive and affordable tutoring, located at QUT, easily accessible. But you can check all the details out there. But I know most of you guys want me to get started on the content, so let's go. So, very quick thing to remark. Obviously, keep in mind that Spec Math is not meant to be an easy subject, right? Like, I'm not saying that methods is necessarily easy either, but, at the end of the day, it's still, nothing compared to Specialist, which has a lot more stuff requiring you to do. But in saying that, it's meant to be challenging and meant to enjoy. It's not meant to be something that, makes you, just suddenly hate math for the rest of your life. No, it's not meant to do that. It's meant to be a challenge for you to really stimulate your brain a bit more with maths and try to, just go the extra mile. So make sure you remember, you probably picked this course because you actually like maths. Don't let this course, be the reason why you don't. So obviously you've learned heaps as a specialist student because you have to learn all the methods as well. And you've also learned this stuff. So that's quite a lot. And honestly, unit 3 and 4, it's going to give you a lot as well. But I think you should feel pretty proud for getting through all 6 of these really fat topics, and also being willing to do more of that throughout the year. But also keep in mind, on one hand, your marks in Unit 3 and 4 don't count, so if, you screwed up something in there, whatever, big deal. But keep in mind that you're going to, QCA's going to assume that you're good at both methods 1, 2, and Spec 1, 2, and also that you're also doing methods 3, 4 at the same time, obviously, as you go through Spec 3, 4. So the content builds upon a lot of prior knowledge, so if you have forgotten things throughout the year, please make sure you spend some time to, brush it up, or at least try to brush it up along the way, because you never know, you may just suddenly need it before you expect it. But yeah. For Unit 3 for Spec, the main thing I want to be able to cover today is induction, because that's one section of Unit 3 by itself. But then the vectors section is literally more than 1/2 of Unit 3 in itself, so it's absolutely ridiculously huge. And you also have to do a bit more complex numbers in this unit as well, before you get to Unit 4 stuff. That's more or less just a bit of a summary of what you should expect soon. Cool, so at the very least, I do want to get up to where I got up to in the actual lecture, and that was basically right before the vector equation of a line. If I find that I have enough time to go any further beyond that, I will. But if I don't, unfortunately, so be it. We'll start with induction first. And, I did spend a lot of time motivating how induction works, and if you have the time to, You should probably try to go through it yourself, but for the sake of the recording, I'll just summarize the main important bits. Induction is basically a new proof technique that you have not, or you likely have not seen before, and it's sort of based on a concept of recursion, where what you do is that you assume that a statement is true at one stage, and show that consequently, or rather as a direct consequence, it's also true for like a next stage. And it's really closely linked to dominoes for that reason, because when you take dominoes, you know that if one domino falls, the next domino falls. But, I mean, or rather, induction is only recommended for situations where you're dealing with proofs involving integers. Induction is not recommended for situations where you want to prove results are true for real numbers, because the whole concept doesn't really work that easily or that well. So it's more of a technique they use for integer proofs, and in the exam you'll usually be told literally, very explicitly by the examiner, oh yeah, go use induction now. So you'll be told, when it's going to be necessary. But alright, enough of that boring stuff, let's look at a problem. So you're going to be dealing with two applications of induction. The first is in dealing with problems on sum, so this is when you have the sum of terms. And the idea is that you want to show using induction, or rather my question here shows that using induction, you can prove that if you add the sum of the cubes, 1 cubed plus 2 cubed plus 3 cubed all up to n cubed, by some miracle you can get it down to a much more simplified expression as I got here. And induction is more or less a means to an end, so we'll go through how it works. So in induction problems, the first step is to start with a base case, which is, I think, also called an initial step or something. I don't remember what your syllabus terminology is, I apologize. But the idea is that you must explicitly test that the statement does indeed hold for the very first value of n in consideration. And the idea is that if you look at this notation, I say that n is an element of the positive integers. So what I really want, well, rather the first value, the smallest positive integer is going to be n is equal to 1. So therefore I need to test that the statement holds for n equals 1. To do that, well, on the right hand side, it's more or less just a matter of summing n equals 1 in, as I've done so here. On the left hand side, I did receive a question during the lecture I think it's pretty important. And you need to realize that this is in fact a sum of terms. And what it really means is that, well, when n is equal to 1, forget about all of this stuff. This term gets somehow brought back all the way down to only being one single term. So n in the left-hand side really counts the number of terms that we have, as opposed to, what it deceptively looks like here. So when n equals 1, the idea is that we only have one term in the left-hand side, and that one term will be nothing more than the first term, which is 1 cubed. And of course, that's something we can evaluate. We can change it's equal to 1, and we'll clearly, okay, both sides are equal. So that's it. That's basically the first part done. Now, following from that, the next step in induction is to actually make an assumption. So don't worry too much about why it's necessary, like you can investigate in your own time. For now, I'll just say, for our purposes, we'll just assume that this assumption is absolutely necessary. And we just assume that it holds when n is equal to k. So I didn't write n is equal to k here, but what I've really done is that I've subbed n equals k into the expression, which you can hopefully see by comparison. But what you want to do is that you want to now use this assumption, so this is supposed to be useful, and you want to use it to prove that the statement does hold for the next value of n. So if you're currently at k, then the next positive integer after k will be k plus 1. So therefore you have to prove the statement holds if you now sub n equals k plus 1 in. So on the right hand side, what do? Well, wherever you see an n, you replace it with k plus 1. So that's how you know the n plus 1 turns into k plus 2, right? But then on the left hand side, you gotta think. Remember again that n counts the number of terms that we actually have on the left hand side. So if n is equal to k plus 1, then effectively speaking, we should have k plus 1 terms appearing. And well, at the very least, that is shown here, because you can assume that, barring all the dots, hiding all the terms in the middle, the k plus 1th term is the last one. But with sums, a very common practice to do is that not only do you write the last term in the sum, because notice how the last term, the k plus 1's term here, right? Not only do you write the last term, but you also write the second last term. And the second last term here will be in the term for where you have k subbed in instead. So like the term before k plus 1 cubed is just going to be k cubed. This is just a very common practice. And the reason why we do it is more or less because we're about to do a substitution. Like, we can then sub... my clicker's not working. We can sub all the stuff over here into that, or rather, the first k terms. So it's more or less just convention to make things more obvious to the examiner, if you will. Oops, wrong way. I'll go back to that. So when you sub it in, you now obtain this by just literally copying the thing in. There you go. Okay, but then what? So what you want to do is that you want to prove that this expression you have right now is equal to this expression over here. So there is a naive way of doing this, and obviously, I'm not going to do it by hand, but the naive way says, okay, you know what? I'm literally just going to expand that whole thing out. That's what I'm doing here. It's just a very, very long expansion, and I'll simplify it. And then you know what? I'll do the exact same thing on the right-hand side. The right-hand side looks like this. I'll do my best to explain the damn thing out. And you see, after all of that work, you do actually get two expressions that are equal. Oops, ignore the typo, but otherwise they're the same. So, that more or less is a proof, because you checked manually that the left-hand side and right-hand side both equal to something else, and that something else is the same, right? So that is one way of doing it, but as you can see, it's not really a pleasant way, because it requires a lot of, expanding, a lot of patience, a lot of making sure you don't make errors along the way. So instead, like what we'd like to do is that we like to use algebraic tricks instead that are more effective. And that algebraic trick that's more useful is factorization. If you look very closely at the expression that we obtained on the left-hand side, you will hopefully find that... So this may be really hard to see. On one hand, k plus 1 squared is a common factor in both terms. Here, k plus 1 squared is a factor of the first term very clearly, but it's also a factor of the second term because k plus 1 cubed can be written as k plus 1 times k plus 1 squared. So what do I do? In the next line, you'll find that I will actually factor the k plus 1 squared out. Now, don't worry too much about it yet because I have one more thing to explain, but that's one part of the puzzle. The next part of the puzzle is that if I look at what I'm trying to prove, I notice that 1/4 is a constant appearing out in front. So ideally, if possible, I would like to factor out 1/4 as well. Here, I can factor out the 1/4 very easily because it's staring right back at me. But here, it might not be so obvious, and it's easier to think about it backwards. The idea is that if you want to factor out 1/4, well then what you can do is that you can rewrite, a 1 here as 1/4 times 4. So what I do is I multiply 1/4 to this expression, but then I multiply 4 to it later on. And notice how ultimately that does not change my expression. I'm literally still dealing with 1 in that sense. So I do that, and then what happens is, well now, because the 1/4 is here, and the k plus 1 squared is here, I can now factor it out of both terms very carefully, and then this is the stuff that I'm left over to fiddle around with. Is that any good? Well, the answer is yes, because when I try manipulating that, I can actually get it very easily down to what I was aiming for. This is nothing more than just a perfect square, so hopefully you can see that very clearly. So that's basically the tough part. The inductive step is something that, it really takes a lot of practice before you get really accustomed to. In the long run, you should find that it's definitely a lot of free marks, it's just the same procedure over and over again, hence that's why it's okay. But in saying that, it's perfectly understandable that most students actually need to have practiced induction often enough for these tricks to really start becoming obvious things to them. At the start, these tricks are not obvious at all, but with enough practice, you start seeing the same pattern over and over again, and things get a lot easier. So there you go. And I'll just make a remark, often it's it's just good practice to, write a concluding statement. I usually just say something along the lines of this to finish my inductive proof off. Do I believe you need to do that for the exam? I don't know. It's mandated in New South Wales, but I don't know what the QCE will require that you guys do. But it's just something I'll make as a mention anyway. Now, I'll go back to the thing that I skipped. Here we go. Also, what I recommend is that until you become used to saying induction, actually write this out. Write out what your final objective is. Write it out so that you know clearly enough what it is you're aiming for. You try to start with this, and your aim is to get to what's over here. Some people that are really good at induction, like me after a few years, try to do it all in my head, but I don't recommend that at the start. The KQ term I've written out before, and also I've more or less been focusing on just the inductive procedure. You'll find in the specialist notes publication that I go through this thing in a more formal manner. Do I believe QCAR require you to do that formal manner? I hope not, but I can't promise anything, so that's why I did it there. For the sake of the recording and the lecture, I'm only interested in how to actually do the problem, so I haven't really talked about it for now. Alright, and then I did look at another problem, but I don't think I will spend too much time on it. I will mention that this problem is definitely very, very long compared to the previous one. It is bloody huge. But it more or less follows the same procedure as the previous ones, just that requires just a bit more involved ultimately. So, similar to the previous one, I start by testing when n is equal to 1, because that's the smallest positive integer. It is the smallest positive integer, I'm sorry. I don't know why I keep exaggerating that. So you test it, and then you check that it indeed is the same value. So therefore, statement holds when n equals 1. Cool, move on. Now you make your assumptions. So you assume the statement holds when you sub n equals k into here. And for the record, you may want to either take a screenshot here or copy this down, because in the next slide, I bring it back up again. This is ultimately what we're trying to prove. And this is what happens when instead of n equals k, I now sub n equals k plus 1. And notice how the left-hand side is such a disaster. It's so long, and it has to equate somehow to this expression. But in a very similar way to the previous problem, this entire garbage here will be subbed out using the assumption. This is literally what we always do. And yes, you'll find that when dealing with problems involving sums, you can usually use the assumption immediately. So you obtain blah blah blah. And now, well, this problem is pretty difficult, and the idea is that, you see algebraic fractions here, so you may be thinking, well, there's really nothing better for me to do when it comes to algebraic fractions, but to literally, just combine the fractions together. That is a transition from line 1, 2, 3 to line 4. And then once you're here, I thought, well, okay, I'll look at what it is I'm trying to prove again. In what it is I'm trying to prove, I have a 4k plus 2, k plus 3 on the denominator. I thought, well, okay, I can pull that out from the denominator here as well. And so I did. So that's more or less the transition here. You'll notice that I am still left with a whole bunch of garbage over on the right, but at least this stuff's now been sorted. Now, remember with induction, you always have an end goal. Your end goal is in fact this thing. So seeing as though we have this bit all sorted now, you may be wondering that, well, can I now get that bit somehow sorted? And that's more or less the puzzle. We more or less have to play around with this thing on the right, and make that somehow equal to this. Which, let me tell you now, is very, very disgusting, because you need to use, guess what you need to use? Polynomial long division. Or at least that's the most straightforward way, which sucks. Right, because nobody wants to do that. So we'll just take for granted that the polynomial long division works. But the idea that when you do that, you realize that this entire expression simplifies down to just being k squared plus 5k plus 4. Which is really brilliant, because when you do that, k squared plus 5k plus 4 literally factors into what you want it to be. So you might need to flip back a few slides. But this is literally what we were aiming for. And well, basically once you're here, that's more or less it. You finish the problem. But notice how it was a huge trek to get there. Alright, so that's application number 1. Now, application number 2 is to divisibility test, so let's talk about what's going on here very briefly. Sums are kind of self-explanatory because all you're doing is you're adding a bunch of terms. Whereas a divisibility test is basically a way of checking if a number is guaranteed to be divisible by another number without actually having to pull out a calculator or manually compute it. So for example, these are some primary ones just to motivate what's going on. For example, a number is divisible by 5 is last digit 0 or 5. Surely we all knew this. A number is divisible by 2 if and only if its last digit is 0, 2, 4, 6, or 8. Surely we knew this as well. Perhaps a less common one, which you may or may not have known, is that a number is divisible by 3 if, when you add all the digits of the number, you get a new number that's also divisible by 3. And that's just a quirky fact. But the thing is, these divisibility tests act under the assumption that you already have a number to begin with. What if instead of a number, you had an expression? So what if instead I wanted you to prove that the expression n cubed plus 2n is divisible by 3 no matter what positive integer n you substitute in? That's my problem. And of course, now this requires a lot more work. So how we do this is that, well, the induction turns out to follow the same procedure, like we need to do our usual base case, and then we need to do our assumption, and then we need to do the special part where we prove n equals k plus 1, which is known as the inductive step. So we need to follow all that procedure, so let's start by checking, well, when n equals 1, well, what does this equal to when n equals 1? Well, if you plug n equals 1 in, you will get 1 cubed plus 2 times 1. Surprise, surprise, that's equal to 3. And well, 3 is obviously a number that's divisible by itself, so that's helpful. But it's just common practice to write that it's equal to 3 times 1 to make it really, really obvious that it is divisible by 3. But I mean, nonetheless, you've more or less checked the statement holds for n equals 1, as you were hoping for. So the base case is pretty easy here. Now, how the inductive step works for divisibility is a tiny bit different in the setup. So for your assumption, what you need to do is that you need to assume when n equals k that, well, that means that k cubed plus 2k should be divisible by 3. But usually you want to represent this in a more algebraic form. And to do that, you need to say, well, therefore, that expression should be equal to 3 times another integer. That's our get around, basically. Once we do that, we need to then prove that the statement, in fact, also holds when n equals k plus 1. I.e., when I sub k plus 1 in, I get something else that is, in fact, also divisible by 3. And I mean, notice how, the expression's a lot nicer this time. It's not as messy as sums. But you'll find that it does require a tiny bit more work algebraically. But at least make sure you understand the setup before you move into the proving part. So, well, the idea is that at times like these, there's not really that much you can do, but to start by just expanding what you've got. So this expression can be expanded like follows. So I use the binomial theorem to expand the perfect cube, and then I'll expand this one normally in the next step. However, often when it comes to dealing with divisibility, it's not, sometimes it's doable, but I generally don't like to use what I've assumed in its raw form. Reason being, although I can make k cubed plus 2k appear, I would rather not, because it's easier to just get k cubed by itself to appear, and instead, I just manipulate the assumption instead. I just rearrange this equation into something else. In particular, what I'll do here is I'll rearrange it into being k cubed equals 3m minus 2k. So I notice how I move this 2k term over to the other side. Once I do that, I can now just literally substitute my k cubed out for 3m minus 2k using my assumption. And that's a transition here. And usually after all of that, what's left for you is indeed just a whole bunch of simplifying. And, well, you find that simplifying is good because when you do simplify it, surprise, surprise, you get to this expression here, and observe how 3 is very clearly a common factor of all of these terms, so you can factor it out in front, right? Is that helpful? Absolutely yes, because we literally wanted to prove that this statement was divisible by 3 to begin with. And notice how what we've done here is that, here's the trick. This expression, well, n we know is an integer from the previous slide. K is also an integer. So therefore k squared is also an integer. And obviously when you add a whole bunch of integers, you just get what? A new integer. So this expression is now literally equal to 3 times another integer. That is the criteria that we needed to satisfy to check that, the expression is indeed divisible by 3. It needs to equal to 3 times another integer. And that is how the proof more or less works. This is basically everything that I've spoken out loud, converted into mathematical format. And again, you should really conclude with a statement, but I won't worry too much about that now. I'll just show you another example. So this example is, again, another divisibility example, but it shows you a different setting because this one, if you notice clearly, is just a polynomial, it's just a cubic expression. This time around, we're dealing with exponential functions instead. So I just want to talk about one of these just in case. And here we're trying to show that this big boy number, 133, divides into that expression for any positive integer, n. So what do? Well, you start by doing the exact same thing you always did, and that's to test your initial value. So that's when n equals 1 again. And it turns out that when you sub n equals 1 in, you get 121 plus 12, which is equal to 133. And well, surprise, surprise, 133 equals 133 times 1. So clearly 133 is divisible by 133, and therefore the statement indeed holds true as well. And, okay, so this is just me being a bit extra by using the quantifiers, but it really just saying the same thing here. And I apologize, that should be capital M here. But what we do now is that we assume that when n equals k, you can then express 11 to the k plus 1 from subbing n equals k in, plus 12 to the 2k minus 1 from subbing, again, n equals k in, equal to 133 times another integer. Once you do that, you need to then prove that the statement is true when n equals k plus 1. So basically the setup is all the same, but I will mention one thing, however. This k plus 1 turned into a k plus 2. And that should be pretty obvious, because obviously, you know, when you sub n equals k plus 1 in, you get k plus 1, and that's where the k plus 2 comes from. Whereas the transition here might not be so obvious to everyone. So you gotta think about it. The idea is that when you sub n equals k plus 1 into the n here, you have to replace n with what I like to say all of k plus 1. So what goes on behind the scenes is that you actually sub in 2 times in brackets k plus 1. So because the k plus 1's actually in brackets here, you need to multiply the 2 to both of them when you expand it. So what happens is that you end up getting 2k plus 2 minus 1. That's why this here is now 2k plus 1 instead of just 2k by itself compared to the previous one. And that's something you gotta watch out for, as I have noted right here. But once you have the setup all done, you now go straight into it. So, your assumption can be rearranged into different ways. You can either make 11 to the k plus 1 the subject, or 12 to the k plus 2k minus 1 the subject. It really doesn't matter which one you use, you'll find that both of them work. For some reason, I just happen to choose this one instead. So we'll roll with it. So I've made 12 to the 2k minus 1 the subject, and here's the thing. If I want to use my assumption, then I need to somehow magically pull out a 12 to the 2k minus 1 from here. Well, obviously I can't pull it out from the first term, so I naturally have to pull it out from the second, but the question is, how? And it turns out that when we're dealing with exponentials, induction problems typically require you to just be really good at your index laws, because step 1 of what you need to do is to just do something like this. What happened? Well, try to think about it backwards. 11 times 11 to the k plus 1 is really 11 to the power of 1 times 11 to the power of k plus 1. So when you combine them together, you get 11 to the k plus 2 using your index laws. Similarly here, well, if you take 12 squared and you multiply that by 12 to the 2k minus 1, again, the powers will combine, you add them together, and that's where you get 12 to 2k plus 1 from. So if you think about it backwards, it might be more easier, but the idea is that we actually have to use the index laws to tear the things apart here, as opposed to, rebuilding them. So that's the first line. Now, from the first line to the second line, all I've done is I've studied the assumption. So this is what I have assumed. Notice how after being clever with index laws, I've now gotten this to appear, so I can now sub it away. There you go. Okay, but then what? Well, now you really have nothing better to do than to just expand that expression out. So please be careful when you expand it out. Observe that here, when you expand it out, you get 144 times 133m. But because I'm trying to prove divisibility by 133, recall that, so like the fancy terminology of the commutativity of multiplication, but just recall that when it comes to multiplication, you can just swap two things around. So therefore, 144 times 133 is literally the same thing as 133 times 144. So I just did a bit of a switcheroo here. And that's that. The other term, well, that one, I just literally left the 144 in front for now. I'll deal with it in a moment. How I will deal with it is that now, so I'll leave this one alone for the time being, but if you look closely, this term and that term are actually like terms in algebra. So if you're not convinced about this, I would recommend making a substitution to something like let u be equal to 11 to the k plus 1. Then you'll find that here you will obtain 11 times u minus 144 times u. And that's hinting that now you can just do basic algebra and just subtract. So 11u minus 144u is going to be negative 133u. But here I basically just chosen to not do the substitution because we're special students, so we can jump straight into it. And well, we get to minus 133 loss of that. But now, surprise, surprise, 133 is in fact a common factor, just like how we dealt with in the previous problem. Alright, so obviously that was a lot, and again, let me reiterate, please pause the video. I do apologize for not mentioning that enough during that section, but again, emphasis, pause the video wherever necessary. But of course, for the sake of the recording, I'm just going to continue. So I do have a little bit of extra advice I do want to mention to the specialist math students, because of course you guys are, doing a lot more work. At the very least, you're doing methods units 3 and 4 as well, and who knows, it may be some of you that are like me and will probably even do general on top of that. But in either case, you're doing a lot of math, so of course, it's going to be hard. Now, the golden rule for dealing with multiple math subjects, at least in my opinion, is this: study for them separately. So a common thing that students like to do is they're just going to say, oh hey, I'm going to go study math now. And what happens is that they're going to start studying for only methods, or only spec, and thus they get a really good mark in one of them, and a really, well, not really bad mark per se, but just a, a disappointing mark in their standards for the other one. And believe it or not, it is a real thing, even the other way around, because if you study too much spec, you may find that you forget all the basics. And of course, if you study too much methods and ignore spec, that's self-explanatory. But it is a real issue, so all I had to say for that is just study for them separately. Make sure when you do study timetables, or study scheduling, or, just think about what you want to study, be explicit about if you're going to study math methods now, or math specialists now, so that you focus on only one thing at a time and not both. But as long as you keep, and keep thinking about that, you should be all good. And that's basically just a more extensive version of what I said just now. Silly mistakes. So, fun fact about me, when I did my final exam for our equivalent of spec math, a bit higher, but same idea, I ended up trying to, buy my marks back. I lost 7 marks in the entire paper, and 5 out of those marks were lost because I did something stupid. Not because I didn't know the content, but rather because I did something stupid. And this happens a lot to higher students, because you get really good at the stuff. And, yes, at some point, your brain capacity might reach its peak, and it might not be able to retain that much more stuff anymore. Things happen, that can't be helped. But then you end up losing so many extra marks due to little things like, for example, not, not flipping the sign when dealing with inequalities, and, when you multiply a negative number, you're going to flip the sign, forgetting to do that. Forgetting to copy a plus or a minus down the next line, so, if a minus turns into a plus, oops. Even little things like accidentally writing a y instead of an x, or later on throughout the year, you may find that you don't differentiate properly or integrate properly, just make a silly error despite, your formula sheet being there, just copied it out wrong. Just little things like that, they're really, really annoying, and honestly, you'll find that they probably hurt you a lot more than, not knowing what's going on once you get your marks back. You really don't want to be there, obviously, because they're not marks you deserve to lose. So, the main habit to get used to here is to get used to checking your paper, and checking is not something that's very easy to do. Like, when I get an assessment task, after I finish the paper, I do not want to see it ever again. Trying to make myself actually check all of my answers, see if they're actually correct, is very tedious, and I find it really, really hard. But nonetheless, it's absolutely mandatory, and still, despite, losing so many marks, checking does help, because I always typically find at least one error by going through my working out, at least that once more. So it's a habit that you need to get used to. Of course, it's not very easy to get used to, so you can start practicing it by, for example, when you're doing textbook problems, when you do a textbook exercise, don't look at the answers until you finish the whole thing. That's one suggestion. But otherwise, just come exam time, something to really watch out for. I won't go too much on about this, but like some really talented mathematics students, what they like to do to really get the extra edge is they like to think a bit more outside the box. They like to think about why something works, because it's one thing just to know how to do something and just roll with it. It's another to understand the intuition behind it and why a certain method is more powerful than another, depending on the situation. And believe it or not, knowing the why can actually help you build more intuition. So like when you see a problem that you've never faced before all your life, you may be more prepared to deal with it because you've seen at least similar problems, and because, you understand the intuition behind how similar problems work, you believe that a certain method up your sleeve is probably the best for that question. And just one little thing, every now and then the algebra might get disgusting. You might get a whole ton of terms that just don't, do a lot that they want to. But every now and then, please be brave, because sometimes just being patient about it, waiting it out, and just going through all the algebra will actually get you to the answer. It's happened to me surprisingly a lot. I just have like huge lines of mathematics in front of me, but it ultimately simplifies it down to something very easy, like for example 1 or x. So yeah, be brave. Alright. Cool. So we'll talk about vectors now. So basically during the time that this thing was all produced, there was stuff I was not comfortable with in the vectors topic, namely how polar forms work in the three-dimensional context. So I don't really cover that right now, but I do cover a bit of all of the other stuff that I know I can cover during this time. And pretty much the first stuff I need to just introduce you guys to is really just basically dealing with vectors in the 3D system. And the 3D coordinate system is different in that you now have a z-axis appearing. So what happens is that the x-axis, usually it now serves the role of how in the 3D system, in practice you can now move forwards and backwards. This is something that we did not have in the 2D system, but in the 3D system it's very important. So forwards and backwards are typically captured with the x-axis. Occasionally can be done so with the y-axis, but at least that's what I've seen so far. Whereas what I often see with the y-axis, now the y-axis reflects your traditional left and right motion, so going this way or that way. And your z-axis will always reflect going up and down. That's something that is pretty much just standard. I will note that in my slides and also in GeoGebra, you'll find that the 3D system looks sort of like this, where you have a bit of an angle here going on. This is just like one of many perspectives you can use, but I will make a remark that there is also the other case, which is known as basically an orthogonal view, where what happens is that it looks something like your y and z axis look like that, and your x-axis somehow protrudes out this way. That's also something that you'll see pretty often, in fact, perhaps more often than not during your studies. So that's something I want you to at least be aware of. But due to limitations of technology, it's not what's going to be used in the slides, and it's also not what GeoGebra uses either. Don't worry too much about the logistics for now. So points in the 3D coordinate system are now basically treated as an ordered triplet. So obviously in the 2D case, when you had x and y, you just had x and y by themselves. Now you need an extra component for the z-axis, and it's pretty much the same thing. Plotting by hand in 3D is usually a bit really annoying, because you've got to do something like this to help you plot the point. Typically, I doubt they could actually make you plot on the 3D system. That's basically just me showing you how the thing works, so you at least understand it. And well then, from then on, a lot of the stuff is just basically a repeat of Unit 1 work in the 2D case, but now you just bring it to the 3D concept. So vectors are approached the same way. You have your vector from the origin to a point, and that can be represented in column vector notation. This is of course a fancy position vector, but won't worry about that yet. For your standard unit vectors, you still have I and j for the x and y components, but now you need to have a new one, k, for the z component, as you can imagine. That one's going to be new. Equality of vectors is still the same as in the 2D case, because of course you need the same magnitude and direction, but it turns out that this can be achieved by just setting all three of the components equal this time around. So if you have two vectors a and b, you require first component, second component, and third component to be equal. Addition of vectors, it turns out that again you can just add the terms component by component. So you add the first components together, second together, and third together, and there you go. And it's worth mentioning that the whole tip to tail addition that you saw with vectors back in Unit 1, that is still true in the 3D case, so that has not left you. Scalar multiplication, also pretty much the same thing. You just basically multiply the scalar. I think you guys use k more often than you use lambda, but it's just a scalar nonetheless. But you basically multiply that scalar to every component of the vector, including the third one. And the fact that a scalar represents a dilation, that concept has not changed at all either. So here's the vector 2 on 3a. Notice how it's a dilation by 2 on 3, but a factor of 2 on 3a, hence shorter than a, but in the same direction. And of course, if you have a negative scalar, it also does the same old thing where what you do that you flip the vector instead. That has not changed at all either. Component form is pretty much the same thing, just that now you have to deal with the third component and you attach it to the k. That's the only difference, otherwise still the same thing. And addition and scalar multiplication, they're still done similarly, so nothing fancy happens at all here. Vector between 2 points, again, turns out that, if you have the vector between 2 points a and b, then the vector ab is indeed given by b minus a, final minus initial, which is done basically in a similar way to, again, what you saw in Unit 2. So there really is nothing fancy at all here. And it looks like the same thing. And that's a lot of the groundkeeping stuff. And then let's do a bit more stuff. The midpoint, again, still defined by the same formula, half of a plus b. Now, the magnitude is a really interesting one, and in the lecture, I did give a proof about where this formula comes from. I will not have the time to do this in the recording, but I'm fairly sure you can find recordings on that on YouTube if you're really interested in it. That or your teacher will show you. But it turns out that this is basically the three-dimensional version of Pythagoras' theorem, which is used for the magnitude of a vector. And the idea is that you're still just adding the square and putting it on the square root. So you just literally plonk the a3 squared term under the square root and it still happens to work. For the sake of the recording, we'll take it for granted. So when I talked about this during the lecture, half of the audience knew what was going on and the other half didn't. So I don't know for sure if this is something that will be, something that you expect to know rather for the exam. And these are basically just some nice properties of the magnitude that are worth keeping in mind. So the magnitude will always satisfy these properties no matter what. I won't go over them now because, the fact that half of the lectures people didn't know about this, makes me feel like this might not be so necessary, but it's worth mentioning anyway. Unit vectors, same concept, you just divide out by the the magnitude, sorry. And you put a hat on it to denote that it's a unit vector. That has not changed at all either. The scalar product, or the dot product, that is still defined the same way, just that now because you have the third component, you have the A3B3 term appearing here as well. Watch out for that. And in fact, the geometric interpretation is still valid. Indeed, in the 3D case, the dot product can still be used according to this formula to help you find the angle between two vectors, and that's still a really powerful property to note. It's worth mentioning that the scalar product also has a few more properties that are worth, bringing up, but again, I'm not going to go over these right now. And then you have the same concept for parallel and perpendicular vectors. So two vectors are parallel if they're only the scalar multiples of each other, and the perpendicular if and only if the dot product is 0. Nice tricks that still hold no matter what. And so does the projection. So recall for the projection, which apparently you're supposed to write A on B according to your formula sheet. Don't know why. But the formula is defined the same way, so you need to consider the dot product here, and I believe there should be a hat on this B, I apologize for that. So you need to compute the dot product of A with the unit vector in the direction of B. That multiplied to the unit vector in the direction of B itself. And what it physically looks like is that, again, you're trying to push the vector vertically down onto B. So that has not changed either. So, if you know your Unit 1 stuff really well, this will all be common sense. Otherwise, you might want to brush up on it. I reckon I will probably gloss over this kind of problem very quickly, but not really go into much depth, because it's just a classic computational question. But this question basically wants you to find the angle between two, or rather this angle ABC, but using vectorial methods. So what you do is that the idea is that, I'm not even going to really go through the calculations. You need to find two vectors that go outwards from B. So you get the vector BA and BC, since we're interested in the angle ABC over here, right? Yeah, it's not highlighting properly. The angle at B, basically. Oh, also keep in mind that the vectors have to be BA and BC, or they can be AB and CB, so they can both go inwards to B as well. But don't do something like BA and CB, or BC and AB, because in that case, the two vectors are either, one of them's going away from B and the other goes towards B. Make sure you never do that for the scalar product in the angle. Remember that the vectors must both go outwards, or they must both go inwards. And then once you do that, well, now that you have your vectors, you just find the magnitude and scalar product that you require to plug into your formula. So as I've done so here. Once you do that, you can then now just use the geometric formula of the dot product in the same old usual way, and your answer falls out very nicely. Now, this problem I will not talk about at all because it requires too many properties, too many algebraic tricks involving the scalar product and the, the norm? The magnitude, sorry. So I won't talk about that right now. And this geometric proof is a really, really interesting one, which I reckon for the sake of the recording, unfortunately, I won't go in much depth at all either. But the idea is that, well, the reason why I don't want to go into it with much depth is because you do need some of these formulas as well. I believe you need this one somewhere along the way. But the idea is that this is more or less a proof showing you that because AC is a diagonal in this cube, and OE is a diagonal in this cube, but although it might not be obvious from this diagram, it turns out that these vectors are perpendicular to each other, but they don't intersect either. Like, OE actually does not intersect AC, the diagram is deceptive in that regard. But this proof basically shows that you can prove that even if these vectors are not intersecting, they are still perpendicular nonetheless. And the trick was that how you would do this is that you will find the vector AC in terms of these three vectors. So OA is just this vector going from O to A here. And OC is the vector from O to C. And this is the vector from O to G. So these are sort of like unit vectors in some sense. And the idea is that you can write OE and AC in terms of these unit vectors. For AC, that's really easy because you can just use the difference of two vectors, well, the vector between 2 points for formula. Whereas for OE, you kind of had to do a tip to tail where you do OG, GF, FE to get there. So it's a bit of a snake in a way. But then the trick is that because we're dealing with a cube here, and this question really assumes that you know the properties of a cube, you know that for a cube, in fact, you can just replace opposite sides. Well, rather, the idea is that GF and OA are equal and parallel. It's more or less using properties of a square. So that lets you do a whole bunch of substitutions, which basically make everything become a lot easier. And then for part 2, to show that they're perpendicular, you require the dot product to be 0. And this basically now requires doing a heap lot of algebraic work with the dot product. But the idea is that if you're really careful about it, you know that angles in a square are right angles, i.e. you have a lot of perpendicularity going on. For example, OA perpendicular to OG, and it's also perpendicular to OC, and OC is also perpendicular to OG. So if you spend the time doing it properly, a lot of these dot products, we have OC and OG, they're perpendicular, they will all evaluate to 0. So you're literally left with all of the remaining dot products that are not equal to 0, i.e. these two, 1 and 2. But then the dot product of something with itself is equal to the square of its magnitude, and once you arrive at here, you use the fact that all sides on the square have the same length, so therefore these two expressions will actually equal to each other, hence OE.AC equals 0, and there's your perpendicularity. So it is a pretty involved proof nonetheless. Alright, well, judging by the time, I'm not going to be able to chat as much as I hoped about the new stuff, but I do need to talk about vector equations because I covered that in the lecture as well. So vector equations are more or less a different paradigm. So like, we've been used to dealing with what I call Cartesian equations, where we have, for example, y equals mx plus b, y equals a squared plus bx plus c, y equals x cubed, y equals e to the x, and they're all called Cartesian equations because they literally relate the x and y together in the 2D case. In the 3D case, you will be hoping for something that has z in it as well. Now, vector equations instead say, can we instead represent each point on the curve through its position vector, i.e. its vector from the origin? So this is obviously a bit abstract at the start, so we have to see an example. And I will remark that for curves, it's very common to introduce a parameter. So a parameter, loosely speaking, is just a variable and it's a scalar. And in more or less, I mean, what is useful in the real world is that it measures how something changes. But for our purposes, we just assume that it's a variable that helps us give a reference. And these are just a whole bunch of common letters I've seen used for parameters. You might not use all of them. And vector equations, so I mean, I mostly introduced it from a 2D perspective to keep things within familiar territory. But keep in mind that this stuff is pretty general and can be adapted outside of 2D concepts as well, into 3D especially. So in the 2D case, the idea is that the curve is represented instead as this form, where you have a vector r, which is sort of like a function in a way, so r is sort of like f here, and the vector r is dependent on a parameter t. And this thing can then be decomposed into the horizontal component in terms of t, and the vertical component in terms of t. So the horizontal and the vertical components are separate, as is always the case in vectors, but they now depend on what the value of t is, i.e. what the value of the parameter is. And notice how the first component of r is then the x-coordinate and second component is the y-coordinate. That's just basically part of the assumption. So it turns out that, so here's an example of a vector equation, and it turns out that it represents the parabola y equals x squared. How you find it is that, so for a basic table of values, what you do is that you sub just like t equals 0 in there for starters, so here's t equals 0. And then you find that the first component becomes 0, so therefore the x-coordinate is 0. And the second component is going to be 0 squared, but that's also 0, so therefore y will be 0 when t equals 0. And that point will then correspond to the origin, of course, because that's, x, y both equal to 0. And then for a more interesting value, let's say we now sub in t equals 2. Then we would obtain the first component is now going to be 2, so that's 2i there. So the x-coordinate of the point will be 2. And then the y-coordinate here will require t squared on t squared here, but when t equals 2, t squared equals 4. So therefore the y-coordinate will be 4. And so therefore you end up with a 0.24 also on the curve. And it just turns out that if you do the same thing over and over again, you'll eventually get the parabola y equals x squared, just like you were hoping for. This example shows how you can, in fact, use a different vector equation to get to the same curve. So surprise, surprise, this vector equation will actually give you the curve y equals x squared as well. But the table of values will look different because when t equals -1, you get these values, whereas when t equals -2, you get those values. How it works intuitively is that this is more or less what's called rescaling the parameter. Like, basically what happens is that if you try doing t equals 2, 4, 6, 8 for this example, you'll get the same as t equals 1, 2, 3, 4 for that one. But then the points, the x and y coordinates will be the same nonetheless. So you get the same curve. It's just that the role of the parameter has changed, and for the sake of a recording, we won't go into that in too much depth. But it's worthwhile mentioning that, again, different vector equations could ultimately give you the same curve nonetheless. And in fact, vector equations are really versatile because you can also get very weirder curves appearing as well. For example, this one here, you now have the circle. It's going to be a very common one that you'll see throughout the course, I imagine. But we won't go into too much about how it's generated here. It's, a bit involved for just like considering I only have like a few more minutes left of talking. And then it is worth mentioning in that it is possible to go back from a vector equation to a Cartesian equation for many examples in the 2D case. How you do that is basically something on the following. What you do is that you set x to be the first component and y to be the second component. Naturally, in the 3D case, you would also set z to be the third component, but in the 2D case, we don't have that, obviously. And then what you do is that, more or less to go back into Cartesian form, your objective is to use techniques of simultaneous equations to get rid of any parameters that you originally had. So here, notice how we originally had a parameter t. Our goal is to basically somehow get rid of the t. And for this particular problem, the easiest way to do that is by just simply making t the subject of that equation. So you get t equals 2x, which you can now sub into that one, so therefore you get y equals 2x squared on 4. And eventually you do end up with y equals x squared, so it all works out for you in the end. There are also examples involving trig functions that you may bump into, as with the circle just now. And in general, the trick for when you have trig functions is to use the Pythagorean identity. So here I use that fact that cos squared theta plus sin squared theta equals 1. You may bump into tan squared theta plus 1 equals sec squared theta as well, possibly. But what you do, basically you just follow the same routine. You make cos theta the subject of the first one. Notice how here the first component is 2 cos theta, so therefore I set x to be 2 cos theta. So therefore your cos theta equals x on 2. You do the same thing for the y component, and you get sin theta equals y on 2. And then you sub both of these back into this equation, and you can more or less rearrange it to get the equation of a circle with radius 2. Now, although I really probably won't go into too much just about how they work, I will mention that throughout the course, it's likely that when dealing with vector equations, you'll be bumping into restrictions on the domain for the parameter of interest. So here, like technically speaking, you could restrict t to be only between 0 and 1, and then you will only get like a part of the parabola. And here you can also do some domain restrictions on theta to obtain any bits of the circle. For example, it just so turns out that in this specific case, you end up with a semicircle instead. But again, these are things that I leave for you to explore throughout the course. And no, don't worry too much about this slide. And I will keep in mind that conversions are not always possible. Like, I've shown you 2 examples where the conversions are really straightforward. And as far as QCEE are concerned, you only need to handle the cases where the conversions are straightforward. But it turns out that in practice, you may get really, really bizarre curves like this spiral here, where trying to convert to a Cartesian form, I promise you, will be very, very ugly at the very least, and probably not even worthwhile. So vector equations are indeed useful because they allow us to describe curves that would not be doable with Cartesian means, but in saying that, there are also Cartesian equations that cannot be described using vector means, so, it's a bit of a trade-off here. But it's just a nice thing to know about. And seeing as I'm running out of time, let me just check that there's nothing more to cover. Yep, cool. So I will mention that also in the 3D case, believe it or not, when you're dealing with curves in the 3D case, vector equations are absolutely necessary. There is no real way of using Cartesian equations to describe curves in the 3D framework. The exception is the case of a line, which I talk about in the slides I'm not going to cover today. But even then, those techniques are really, really bad. You're expected to know them because they're really, really useful, but they're not really tidy. They're, really ugly. And so, therefore, usually, to keep things as nice as possible, you'll be bumping into vector equations a lot in the 3D case. For example, here we have the circle in the xy plane. You'll learn about planes later on. And that's radius 2. And then what I can do here is that for this example, I'll now turn the z component from 0 to 1. And that just basically translates the circle up by 1, but it still has radius 2. But again, using these vector equations was absolutely necessary to properly describe the circle. And I doubt you'd be expected to actually graph it anyhow, because it'll be too much of a hassle. So pretty much that's all I'll be covering for today's recording. Of course, there's still a lot of stuff that I didn't talk about, so if you have any more questions about it, please jump on the forums. Even the stuff that, I haven't covered during the lecture or the recording, if you want to ask about that on the forum, please don't hesitate to do that. I've linked it here for you. But yeah, I reckon that's all I have for now, so thanks guys for tuning in for so long. I really appreciate it, and hope you guys stick around and enjoy more stuff that we do here at ATAR Notes.